this is Naresh, working as assistant professor in AEC department. So today's topic is problems on xenon diode regulator. So in this session, we are going to discuss some of the problems on xenon diode as well as voltage regulator. So first we will see the one problem. Design a Zener shunt voltage regulator with the following specifications. And the given specifications are the Zener means the output voltage is 10 volts and the input voltage lies between 20 to 30 volts and the load current lies between 30 to 50 milliamperes and the Zener current is means the current across the Zener diode is 20 to 40 milliamperes. So in that they given that means 30 to 50 milliamperes means the load current minimum as well as the load current maximum means where so the ideal minimum value is represented as 30 milliamperes and the load maximum current is represented as 50 milliamperes. Similarly, the current across the Zener diode is the Zener minimum current is 20 milliamperes and the current across the Zener, the maximum Zener current is 40 milliamperes. And similar to that, they given that the Vin is lies between 20 to 30 volts means the Vin minimum value is 20 volts and the Vin maximum value is 30 volts. So for all these given specifications, the Zener diode regulator produces a output voltage is 10 volts. So hence, so based on these specifications, we need to design a Zener shunt voltage regulator means we need to identify the resistance, series resistance as well as the load resistance means how much series resistance is required and how much load resistance is required to produce all these specifications like the output voltage is 10 volts and the load current is 30 to 50 milliamperes and the Zener current is 20 to 40 milliamperes. So hence first I noted down this given specifications here. The output voltage is 10 volts and the input is lies between 20 to 30 volts. The load current is 30 to 50 milliamperes and the Zener current is 20 to 40 milliamperes. So first from the given Zener diode means so shunt regulator means here I am going to draw this one. Let us say this is the R and we are going to apply a Zener diode. So let us consider a load resistance RL and here we are going to find out the output voltage and we are applying the V in here. This is minus and plus. So and based on that the output voltage means parallelly the voltage is the same, hence the voltage across the Zener diode, that is the voltage across the load resistance, that is the output voltage is equal to 10 volts. Now, and from the given specifications, we observe that the maximum Zener current is represented as 40 milliamperes. So hence, now we are going to calculate how much power is produced by using the Zener diode. Means, so we know that generally P, the power is representing the product of voltage and current. Hence, here the voltage is represented as Vz and the current is represented as Iz. And here we know that the Vz is 10 volts. So it is multiplied with Iz maximum. So from the given specifications, the Zener current maximum is 40 milliamperes, hence 40 into 10 to the power of minus 3. This is 400 into 10 to the power of minus 3 is nothing but a 0.4 watts. So that is the reason. The power watts across the Zener diode is 0.4 watts. Now similar to that, now we need to calculate the load resistance value RL to observe this load resistance value, we need to find out with respect to the minimum and maximum ends. So we need to find out the range, how much resistance we need to offer to produce a minimum load current as well as the maximum load current, that is lies between 30 to 50 milliamperes. Hence, to determine this minimum load resistance, so in general, R is nothing but it is a ratio of voltage to the current. So while calculating this minimum resistance, it is defined as it is a ratio of output voltage to the load current maximum. Hence, we know that the output voltage is 10 volts and the load maximum is 50 milliamperes, means 50 into 10 to the power of minus 3. Then you can solve this ratio. It gives that the RL minimum is 200 ohms. Similar to that, we need to calculate the maximum load resistance. Hence, the maximum load resistance is defined as it is a ratio of output voltage to the load current minimum. So then the V0 is 10 volts divided by IL minimum is, so from this we are representing this, the minimum current is 30 milliamperes and the maximum load current is represented as 50 milliamperes. So hence the IL minimum is 30 milliamperes. So hence 30 into 10 to the power of minus 3. So hence then while solving this ratio, it gives that the RL maximum. So this RL maximum gives that 333 ohms. Hence, while choosing the load resistance, RL value is lies between 200 ohms to 333 ohms. So if you observe, the RL minimum value is 200 ohms. Hence, the RL maximum is represented as 333 ohms. Hence, while choosing this load resistance, the load resistance is lies between 200 ohms to 333 ohms. Then after that, we need to calculate how much input resistance is offered to produce the given specifications. Hence, I am now going to calculate the value of input resistance R. So from this, the R should be defined as the potential difference between the Vin maximum and output voltage to the IL minimum and IZ maximum, the summation of load current minimum and the Zener current maximum. So from this, the Vin maximum, so from this we can say that the Vin minimum is 20 volts and the Vin maximum is 30 volts. Hence, the Vin maximum is 30 minus V0 is 10 volts divided by IL minimum is 30 milliamperes, 30 into 10 power minus 3 plus IZ maximum is 40 milliamperes, means 40 into 10 power minus. So hence 30 minus 20, 10 is 20. This is 70 milliamperes. Then by solving this ratio, it gives that the R maximum is 286 ohms. Similar to that, we need to calculate the R minimum value. So to calculate this R minimum, we need to consider the Vin minimum, and along with we need to consider the load current maximum and the Zener current minimum. Hence, the Vin minimum value is from this. The Vin minimum value is 20 volts. Hence, this is 20 minus this is, so 20 minus V0 is 10 volts divided by IL maximum here. So that is 50 milliamperes, 50 into 10 power 3, and IZ minimum is 20 milliamperes. And this is 20 minus 10, 10 by this is 70 milliamperes. Then by solve this ratio, it gives that the R minimum is 143 ohms. So that is the reason. Again, while choosing this R resistance, it should be lies between 143 ohms to 286 ohms. So that is the reason. We need to choose the range of input resistance is 143 ohms to 286 ohms. Then while taking this one, here I will consider the average value of this maximum and the minimum. So by substituting this maximum and the minimum values, so 286 plus 143, so this is 286 ohms and minimum is 143 ohms by 2. By solving this one, the R should be 215 ohms. So the nearer value is, you can consider up 220 ohms. Then if you want to draw this one, the ends we need to take this R value is 215 ohms and the Zener diode, it should be operated. The power is 0.4 volts based on the given specifications, and we need to consider this is the load resistance. Then we need to apply a Vin, this is minus and plus. So here the load resistance is represented as RL is 200 to 333 ohms. So here we need to consider the value is 200 to 333 ohms. Then it produces a output voltage is 10 volts. So that is the reason. So here this is the given circuit. So if the diode is a reverse bias means we need to connect. So positive is always connected to cathode, negative is connected to anode. This is for a given design configuration. Now you will see another problem. In a Zener regulator, the DC input is 10 volts plus or minus 20%, means the tolerance is the 20%, means the input voltage. So for this case, the 20 volts, 10 volts. So in that 20% means, so 2 volts is a plus or minus, means the minimum value is it becomes 12 volts and the maximum is becomes 14 volts. The output requirements are 5 volts, 20 milliamperes. So these are the outputs. V0 is 5 volts and the current, the load current or I0 current is represented as 20 milliamperes. Assume the Zener minimum and the Zener maximum is 5 milliamperes and 80 amperes. So from that, the minimum Zener current is 5 milliamperes and the Zener maximum current is 80 amperes. Then we need to design a Zener regulator circuit for these given specifications. So that is the reason I represented the given specifications. The input is 10 volts plus or minus 20%. V0 is a 5 volts and the load current or output current is a 20 milliamperes. IZ minimum is a 5 milliamperes and the given IZ maximum is 80 amperes. Now first we need to find out how much the minimum Zener current for this case. So and this should be generated when the input voltage is maximum, then the Zener current provides the minimum Zener current, that is 5 milliamperes. So for this case, hence the input voltage varies between, so that is a plus or minus 20%. So means the 20% means 2 volts, means minimum value is 10 minus 2 as well as 10 plus 2 means 8 volts and 12 volts here. The minimum voltage is 8 volts and the maximum voltage is 12 volts, means the Vin is lies between 8 to 12 volts. That is a given input voltage. So therefore the Vin minimum I need to consider 8 volts. So hence the V minimum is 8 volts and the V maximum is 12 volts. Now we need to calculate the load resistance as well as input resistance while designing this Zener diode regulator. So to calculate this RL, so now we need to define it is a ratio of output voltage to the output current. So if you observe the given circuit, let us take this is R and the Zener diode is connected in a reverse bias. So hence this is Vin plus and a minus. Now we are going to place a load resistance RL. So now this is V0 is represented as 5 volts. So across this load resistance, the load current is represented as 20 milliamperes. Now we need to calculate how much resistance is required to satisfy this load current is 20 milliamperes and output is a 5 volts. Hence it is defined as it is a ratio of output voltage to the output current. So here the V0 is 5 volts and the load current is 20 milliamperes. So means 5 by 20 into 10 to the power of minus 3. Then it gives that the RL is a 250 ohms. Now similar to that, we need to calculate RL maximum. So if RL maximum, that should be connected by V0 by IL minimum. So and here actually there is no need to calculate this RL maximum. They are not given this IL minimum. So only we need to calculate RL. So that is RL is equal to V0 by IL. So hence that is 5 volts divided by 20 into 10 to the power of minus 3. That is so 250 ohms means RL is 250 ohms. Then we need to calculate the input resistance R. So we observe this RL is 250 ohms based on the given specifications. Now we need to calculate the input resistance. So to observe this input resistance is represented as R is equal to the potential difference between Vin minimum and output voltage to the IL and IZ minimum. And we know that the minimum given voltage is 8 volts minus V0 is a 5 volts divided by the load current is 20 milliamperes plus your Zener minimum current is 5 milliamperes. So this is 8 minus 5 means 3 divided by, so this is 25 milliamperes. So from this we need to determine the R value, that is by solving this ratio the R value becomes 120 ohms. Hence R is equal to 120 ohms. So RL value is 250 ohms. Then R is a 120 ohms. Based on this, we need to design a Zener regulator circuit. So hence I am going to take this is R. So R is we determined as 120 ohms. Then parallelly I am going to place a Zener diode. This is cathode and anode. And here we are going to apply a reverse bias voltage. Hence, the positive polarity of the battery is connected to cathode of the Zener diode with respect to the anode. And we are going to place a load resistance RL. Then output is measured across the load resistance. And at this point, the RL is, we observe that this RL value is 250 ohms and R is observed as 120 ohms. And based on these given specifications, this Zener diode circuit produces 20 milliamperes and 5 volts DC output. Now we'll see the another problem. If the DC unregulated input is 20 volts and output voltage is 10 volts, load current is 0 to 20 milliamperes. Design the regulator. Assume for the Zener the IZ minimum is 10 milliamperes and IZ maximum is 100 milliamperes. So here the unregulated input means Vin is represented as 20 volts and the Zener regulator circuit to produce the DC output voltage is 10 volts. And the load current is means the load current is 0 to 20 milliamperes where the IL minimum is 0 and IL maximum is 20 milliamperes. And apart from that, in a given problem, they are specifying that the minimum Zener current is 10 milliamperes and the Zener maximum current is 100 milliamperes. For all given all these specifications, we need to design a voltage regulator circuit. If you observe this voltage regulator circuit, it contains a input resistance that is R, and we are going to use a shunt voltage regulator. So this is Zener diode, anode and a cathode. Then here we need to place a load resistance RL. And if you want to utilize the Zener diode, it acts as a regulator. The Zener diode should be reverse bias. Hence, now we are going to pass or to make the reverse bias. Hence, the negative pole of the battery should be connected to anode of the Zener diode with respect to the cathode. Hence, the positive pole of the battery is connected to cathode terminal of the Zener diode. Then here we are going to measure output voltage is V0. Now first I write down the given specifications. Input voltage is 20 volts, output voltage is 10 and the load current is 0 to 20 milliamperes. IZ minimum is 10 milliamperes. IZ maximum is 100 milliamperes. So for this circuit, so this is a given circuit. So here now we need to calculate R value and RL value. And here the Zener diode is also reverse biased to satisfy the voltage regulator. So hence the positive pole of the battery is connected to cathode of the Zener diode. Negative pole of the battery is connected to anode of the Zener. So for this case, if you apply the KVL to the closed loop circuit, so we know that this is so means the sum current flowing across this resistance along with the voltage drop across this Zener diode that is equal to output voltage. Means we know that the output voltage is exactly equal to Zener voltage in a shunt configuration. Hence V0 and Vz is equal to 10 volts. So if you apply the KVL analysis from this closed loop circuit, so this 20 equal to the voltage drop across this resistance is represented as I into R plus along with the voltage drop across this Zener diode that is equal to V0 that is equal to 10 volts. So hence I consider with the summation of voltage drop across the resistance and the voltage drop across the Zener diode, it is represented as 20 is equal to I into R plus 10. From this, I am going to derive some relation. So 20 minus 10 that is equal to I into R. So hence can I write R is equal to 10 by I. So this is the condition to solve the input resistance. The relation between this input current and resistance R is equal to 10 by I. So from this we observe this one R is equal to 10 by I. Then again let if IZ is equal to IZ minimum and the load current minimum value is IL minimum is 0 from the given specifications, And from this, now we need to calculate the total current, the I is, if you observe this one, the given circuit, the total current I is, means this I is leaving towards Zener as well as the load, means the entry according to KCL, the entry current is equal to the leaving currents. So hence I is equal to, from this, IZ plus IL. So that is the reason we represent it as I is equal to IL plus IZ, where the IL value is the minimum value. So here I'm going to find out the minimum value. So where IL is a 0 minimum. So from this representation, the IL minimum value is 0 minimum, 0 milliamperes. And IZ minimum value is 10 milliamperes. That is the reason 0 plus 10 milliamperes, that is equal to 10 milliamperes. So therefore, now we observe that one relation between R and the current to observe this input resistance, and based on the given specifications, we identify that the relation is between current and R is equal to 10 by I times, means R is equal to 10 by. So your I value is 10 milliamperes, means 10 into 10 to the power of minus 3. So hence R becomes 1000 ohms, or it is also represented as 1 kilo ohm. So that is the reason. From this factor, we identified that the input resistance should be 1000 ohms or 1 kilo ohms. And similar to that, we need to calculate for a maximum. If IZ, we assumed as IZ maximum, the maximum load current is 20 milliamperes when we consider the maximum currents. And from that, the total current again is represented as the summation of the maximum load current and the maximum Zener current. So here we know that the IL maximum is 20 milliamperes. So 20 into 10 to the power minus 3 plus the maximum Zener current is 100 milliampere. So that is the reason that is 120 milliamperes. The maximum current I maximum is 1200. So this is 120. So 100 plus 20 milliamperes. Hence this is 120 milliamperes. The maximum current is represented as 120 milliamp. So from this, we need to calculate the R maximum. To observe this R maximum, we have the one relation, that is 10 by I. So hence the 10 by. So here I value is 120 into 10 to the power of minus 3. So then it becomes 1 by 12 into 10 to the power of minus 3. So after solving this ratio, it gives that R value is 83.33 ohms. That means your R value should be lies between. In a previous condition, we observed that 1000 ohms, and here the R maximum should be 83.33 ohms. Hence, R should be lies between 83.33 ohms to 1000 ohms. So that is the reason. While choosing this the resistance for this Zener shunt regulator, the R values is lies from the minimum resistance to maximum resistance. The minimum resistance here it is observed for a given specification, that is 83.33 ohms, and the maximum is 1000 ohms. So hence R equal to, and first we need to find out the load current. The load current RL is equal to. So your R value should be lies between 83.33 ohms to 1000 ohms, and RL is also. So your RL value is. Now we'll see another problem. Let us consider design a Zener voltage regulator to meet the following specifications. The output voltage is 5 volts, and the load current is 10 milliamperes, and the Zener voltage is 400 millivolts, so millivolts. Zener voltage is 400 millivolts, and the input voltage is 10 volts plus or minus 2 volts. For this given specifications, we need to design a Zener voltage. It means we need to find out R value as well as load resistance value. So based on this given specifications, the VI minimum value is 10 minus 2, that is 8 volts, and the VI maximum value is 10 plus 2, that is 12 volts, and output voltage is 5 volts, and the load current is 10 milliamperes, and the given power specifications are 400 millivolts. Based on this, we need to calculate the load resistance as well as R value. So for this case, from the given specifications, we know that it is a ratio of output voltage to the load current. From this, the output voltage is 5 volts and the load current is 10 milliamperes. Then the load resistance is becomes, so this is so means that is 500 ohms. So this is 5 into 10 power 2. So hence the load resistance. So this is 5 into 10 power 2. So hence the RL value is 500 ohms. The load resistance is 500 ohms. Now similarly, we need to calculate how much Zener maximum current is flows through the Zener diode. And in generally, we know that P is represented as the product of voltage and current. So now here I'm going to calculate current. So hence it is the ratio of power to the voltage across the Zener diode. So for this case, the power across the Zener is 400 millivolts. So that millivolts means 400 into 10 to the power of minus 3 volts divided by the output voltage V0 is 5 volts. So if you simplify this one, it becomes IZ maximum is 80 milliamperes. The maximum Zener current is 80 milliamperes for the given specifications. Now similarly, we need to calculate how much input voltage is required when the Zener current is 0. Under this condition, we know that I is equal to IL, that is equal to 10 milliamperes. So that is the reason I is represented as 10 milliamperes. Now we need to calculate the minimum voltage. So for a V minimum, so it is represented as, means for your given circuit, if you consider this one, this is R and this is a Zener diode. So it is represented as a Vn, and let's take this is V0. If current is flowing across this resistance R, so we need to write this Vi is equal to the voltage drop across the resistance. So that is represented as I into R, along with the voltage across the Zener diode is represented as Vj. So from the given specifications and from the given shunt Zener voltage regulator, we know that the Vz is approximately equal to 10 volts. So hence the Vi minimum is represented as V0 plus IR. So now by using this relation, now we have to choose this one. So Vi minimum is, means from the given specifications, the Vi is varies from 10 for a given voltage is the plus or minus 2 volts. Hence it is 10 minus 2 and 10 plus 2, that is 8 volts plus or minus, means this is 8 volts and this is nothing but a minimum voltage, and the maximum is 12 volts, that is maximum. Now here I am going to substitute the minimum, means 8, that is equal to V0 is a 5 volts plus I into R. So I into R means that is So 10 milli means 8. VI minimum is 8 volts, and V naught is V naught is nothing but your. So here it is represented as 5 volts V naught, and I means, so what is I? That is represented as a 10 milliamperes the load current. So means, so V in minimum, that is equal to V naught plus I minimum into R. Or you can also write IL into R, V naught plus IL into R. So that is the reason I is represented as 10 milliamperes and R. From this we need to calculate. So this is 3 is equal to 10 milliamperes into R. So from this, the R maximum is represented as 3 by 10 milliamperes. R maximum is represented as 3 by 10 milliamperes. So hence that value is equal to 300 ohms. The maximum resistance for a given specifications is represented as 300 ohms. So similar to that, for a maximum input voltage, again we can write from the given circuit. Let's just say this is R, again this is Zener diode under this reverse bias. So here we are going to apply the VI. So under the reverse bias condition, so hence we have the load resistance RL. Now the current flow, if we apply the KVL loop, so we can write this VI is equal to the voltage drop across the resistance is represented by IR, and the voltage drop across the Zener diode is represented as VZ. So hence at this point VI is maximum represented as, that is equal to. So at this point, so what happens, the same current is flowing through this Zener diode. That is the reason we can write this total current is I plus IZ into R plus, and your VZ is that is nothing but VZ is nothing but your V naught. That V naught is equal to 5. So here we need to calculate. So the VI maximum means the tolerance should be plus or minus 2 volts for a given specification, 10 volts. Hence, the VI maximum becomes 10 plus 2, 12. That is equal to V naught is 5 plus, and now we need to substitute I. So I plus IL. So means so it is represented as, so here this V naught is means VI maximum is 12. This is V naught is a 5 plus I plus IZ. So here IZ means that is 10 milliamperes, and this is I means 80 into R. So now we need to calculate this R minimum. So R minimum is divided by, this is 12 minus 7, that is 7 and by 90 milliamperes. To solve this ratio, then R minimum gives that 77.77 ohms. So therefore, the value of this R lies between, so minimum value is 77.7 ohms and maximum is your 300 ohms. That is the region. The range of R varies from 77.7 volts to 300 ohms. Then again, one more problem we are going to discuss. A 24 volts 600 millivolts Zener diode is used for providing a 24 volts stabilizer supply to a variable load. If the input voltage is 32 volts, calculate the value of series resistance is required and how much diode current is flows when the load is 1200 ohms. So now for a given this problem, so it contains a 24 volts 600 millivolts Zener diode is providing 24 volts stabilizer supply, means the V naught is output voltage is 24 volts, and for this case the given input voltage is 32 volts, means VI is represented as 32 volts. Now we need to calculate how much series resistance, that is the R, is required, and we need to calculate the diode current when means the xenon current means, and we need to calculate high Z when the load RL is represented as 1200 ohms. So for this case, I note on these given specifications. The input voltage is 32 volts and V naught is at 24, and they given that the power 600 millivolts. So hence the power across the Zener diode is 600 millivolts, and the given load resistance is 1200 ohms. For this case, now first I'm going to calculate the current across the current across the load resistance, that is represented as for your given circuit. So let's take, and this is the series resistance R, and here we're going to place the RL. Now this is a reverse bias configuration, hence a negative polarity is connected to anode, a positive polarity is connected to cathode. So across this, we are going to calculate how much current is flowing through this load resistance that can be absorbed by, it is a ratio of output voltage to the load resistance. So for this given statement, the output voltage is represented as 24 volts and the load resistance is 1200. By solving this ratio, it gives that the IL is equal to 20 milliamperes. Now we need to calculate how much maximum Zener current. So means IZ maximum means we know that the power is the product of V and I. And from this, I need to calculate this I, and it is represented as the ratio of power to the voltage. So hence I represented as the Zener power to the Zener output voltage, that is V0. So hence the PZ is, from this given specification, the Zener power is 600 milliwatts, means 600 into 10 to the power of minus 3 watts by the V0 is 24 volts. So by solving this ratio, it gives that the IZ maximum is 25 milliamperes. The Zener maximum current is 25 milliamperes. So based on that, now we are going to calculate how much maximum and minimum resistances are required to satisfy these specifications. Hence, if you want to absorb this R maximum from the given diagram, it is represented as V by I, means the potential difference between, we have the two voltage sources. So why it can be the two voltage sources means whenever the Zener diode is operated under the reverse bias. So let us take when the Zener diode is operated under the reverse bias. This Zener diode, whenever it is enters into a conducting state, it should be replaced with a battery or a voltage source. So hence the voltage, if you apply the KVL, the loop analysis, then we are going to find out how much resistance is required. So hence it should be determined by it is a ratio of the potential difference between input voltage and the voltage across the Zener diode, or the output voltage to the IL minimum plus IZ maximum. And now VI is 32 volts and the V0 is 24 divided by IL minimum. So we absorb this IL minimum value and IZ maximum value. So here the IL value is 20 milliamperes. So IL value is 20 milliamperes. This is 20 into 10 to the power means, so IL value is 20 milliampere. And similar to that, we need to calculate IZ. So already we observed this IZ maximum. The IZ maximum is 25 milliamperes. So hence IZ maximum is 25 milliamperes. So hence this is 25 milliampere, means 25 into 10 to the power of minus 3. So this is 32 minus 24 means 8. 8 by 25 plus 20 means 40 milliamperes, means this is 8 by 40 milliamperes. By solving this one, it gives that the maximum resistance value is 177.78 ohms. Now again we'll see one more problem. A Zener voltage regulator circuit is to maintain a constant voltage at 60 volts over a current range from 5 to 50 milliamperes. The input supply voltage is 200 volts. Determine the value of the resistance R to be connected in the circuit for a voltage regulation from load current IL is 0 milliamperes to IL maximum. The maximum possible value of IL. So what is the value of IL maximum? So hence for this given specifications, the input voltage is 200 volt and output voltage across the Zener diode that is equal to 60 volts. Then we need to calculate the value of the resistance. To determine this value of the resistance, and we need to calculate the maximum resistance and the minimum resistance. While observing this maximum resistance, it is defined as is the ratio of input voltage to the output voltage by IL maximum plus IZ minimum. So VA is 200 volts and the V0 is 60 divided by IL maximum. In a given problem, it is given as IL maximum, that is the load current, 0 to IL maximum means the load current is 0 means. So then IZ minimum. So what is IZ minimum? So for this given case, then do over it. A Zener current range from 50 to 5 to 50 milliamperes means that is the maximum Zener current is 50 milliamperes and the minimum Zener current is 5 milliamperes. Hence, so here it is represented as, so VA is a 20 minus V0 is a 60 and IL is a 0. IZ maximum is 50 milliampere. So that is the reason it is represented as 200 minus 60 by 50 milliamperes means 140 by 50 into 10 to the power of minus 3. Then it gives that the R maximum is 2.8 kilo ohms. Similar to that, we need to calculate what is the maximum current. If you assume that if a Zener current is the maximum 50 milliamperes from the given specifications, then we need to consider the load current is 0. IL is 0. For this, again, for similarly, the IZ minimum means the Zener current flows from 5 milliamperes to 50 milliamperes. For this consumption, the Zener minimum current is 5 milliamperes and the IL maximum is 45 milliamperes. So from this, the IL maximum, so we need to choose only the maximum values. So based on that, the load current maximum is 45 milliamperes. So up to this point in this session, we observed that some of the problems on a Zener voltage regulator, then how to identify the input resistances and the load resistances while designing the Zener diode as a voltage regulator circuit. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.